Hi guys, welcome to chapter 3 of AP Statistics. Before I forget, we're going to be doing a ton of work in the calculator and while we take the notes, and you're going to want to save your data sets because we're going to use them again in the next section of notes as well. We're going to use the same data set for a couple different things. So make sure that you go in, you can just, once you start your calculator, like once you start your data, just go hit the doc key, file, save as, and you can just call it what chapter 3 notes or something. That way you don't have to keep retyping in the data. Okay, so today we're going to talk about bivariate data, all right, or data that is on both axes. Okay, and you can see right here we've got a scatter plot. Right, scatter plot is the basis of this whole chapter. So we have our response variable, which goes on our dependent axis or our y-axis. That's the one that measures an outcome of a study. Okay, our explanatory variable goes on our x-axis. Right? So really we kind of want to read them the other way. Does the explanatory variable explain what happens on our response? Does our x-axis explain what changes on the y? All right, and when we graph a scatter plot, I know you guys have done this forever. Years and years, you're going to have, your data sets. So everything's going to be given to you as ordered pairs. Okay. When you put your data in a list, never ever sort it because when you sort it, you're breaking up the ordered pairs. We need to keep them together. So for these types of problems, when you have X, Y axis, never ever put them in order. Okay. Keep them as ordered pairs. Just like when we did one variable data and we talked about center shape spread, when you're examining a scatter plot, you always want to comment on form, strength, and direction right here. Okay, huge deal. Form, is it linear or is it curved? Are there clusters of data together or what? Okay, direction, is it a positive relationship? In statistics, we use association just as much as we use relationship. Okay, so are they associated? And then strength. How close are they together in the form of a line or in the form of a curve, right? If they're really strongly related, they're gonna be really tight knit. Whereas if it's a weak pattern, it's gonna kind of look like pepperoni on a pizza, right? You want your pepperoni all spread out all over the place. You don't want like one line of pepperoni going right down the middle of the pizza and no pepperoni anywhere else. So weak relationship would be like good pepperoni on a pizza where it's just evenly sprinkled all over the place. All right. And then you also need to look at, do you have outliers? Does a data value fall outside the overall pattern of the data? So let's say that I took a small class and I made everyone run a 40-yard sprint and then do a long jump. Okay. And I calculated the sprint. I didn't calculate, but I wrote down the sprint times and the jumps. Okay. The first thing we want to do is we want to make a scatter plot of your relationship. So we are not graphing this by hand, right? I know that you guys know how to graph ordered pairs as a scatter plot by hand. I want to talk to you about how we're going to do all this in the calculator. Okay, so I already have my sprints and jumps written down. I'm going to put sprint on the x-axis and I'm going to put jump on the y-axis. So I typed in my two data sets and I'm going to add a plus page. Okay, and I'm going to graph a data and statistics. Come down here, we've done this before. Now, I just popped up a whole bunch of stuff because I have all my other variables, all right? And then you guys, I will explain what all these mean in the next lesson probably. But I'm going to put sprint on my x-axis. That's a dot plot. If you come over here and you click Y and we want jump on our y-axis, now we have a scatter plot. It does a really nice job. You can hover over them to figure out what each ordered pair is. Okay, so that would be a scatter plot graph. All right, you could sketch it by hand. If you have to actually turn in a graph that you have to sketch by hand, it is wrong if you don't label each axis. So if you don't put sprint and jump, sprint times and jump lengths, your graph would be considered incorrect. Okay, it's extremely important that you graph them. So let's go to the next question. All right, example 2. Describe what the scatter plot in the previous example reveals about the relationship between sprint and long jump distances. Now, when you're looking at that graph, we need to comment on strength, form, and direction, or in any order. Form, this is approximately linear. Okay. Direction, negative. Strength, I would say there's a strong relationship, right? There's a clear pattern that the slower your sprint, right? The higher timings, the slower your sprint, the shorter your jump. The faster your sprint, the farther your jump. All right. So when I look at my description, I actually put it here. As sprint time increases, jump distance drops or is shorter. We have a strong negative. I forgot the word linear when I wrote my answer. I apologize. So I had a linear here. Strong negative linear relationship between sprint time and jump distance. If you write strong negative linear period, you're going to get half credit because you did not include the context of the problem. So make sure it's always in the context of the problem. This is an important statement, right? As sprint time increases, jump distance drops or gets shorter. Or you could go the vice versa. The faster you sprint, the longer the jump is. And you could describe it that way as well. All right. So we made a scatter plot on the calculator. Check. Now let's talk about way more to go with that. Okay. The next thing we can talk about is we can talk about correlation. So bivariate data is the term I had used to describe at the very beginning of this lesson. Okay, bivariate, two variables, right? And we're looking at them together. So when we're looking at this, we also have our correlation coefficient, which is R. Okay, your correlation coefficient is R. Here is the formula to calculate R. Yes, it's on your formula card. No, I have never, ever seen them ask you to do this by hand because this is absolutely atrocious. Okay, you would need to multiply this and this together and then add up all of those multiplications of each data point's x minus the average of x's divided by the standard deviation of x times that data point's y minus the average of the y's divided by the standard deviation of y's. If you have 20 data points, you need to do this 20 times and add it all up. I've never seen that asked ever to do by hand. You can use the technology at all times. All right. So notation. R is what we call a sample correlation coefficient. We always deal with R. If for some situation the data points you had were the entire population, then you would use rho. It looks like a Phillies P, but it's actually rho. That's your population coefficient, correlation coefficient. You don't need to know this. Just wanted to introduce it to you guys, but this is not asked on the exam. Okay, so range of your correlation coefficient goes from -1 to 1. If you have a strong positive relationship, your value of R is going to get closer to 1. A strong negative relationship, the value of R will be closer to -1. Okay. Everyone always asks, like, well, how do you know it's strong or not? Like, what's the number? We will do that. It's actually chapter 12. So chapter 12 gives us an official test to figure out if there's a relationship or not. Right now, we're just kind of eyeballing it, which doesn't always make you guys comfortable, but that's okay. So I'd say like a good estimate is 0.7 or higher, or -0.7 or lower. Absolute value 0.7 to 1 would make it strong. That's like a good guessing range. Okay. Anything else closer to 0 is just not a good, strong relationship. So when you're looking, I gave you guys like a couple graphs. This would probably have like an R equals 0.99. This would be like about an R equals -0.84. All right. -0.2, no pattern. Okay. 0.56, it's strong and it's moderate and it's positive, but it's spread out still. It's not just close to a line, right? You guys have learned line of best fit. That's actually in our next lesson. But if you could think about like the line of best fit, that will make it a stronger R. A tip that you can use if it's a picture pre-drawn for you, you can just draw an oval around the points. The rounder it is, the closer it is to 0. So look, if I drew this, I'd pretty much be drawing a 0, and your correlation coefficient is pretty much 0. Whereas if I drew it here, my oval would be long and skinny. That means it's closer to 1 or -1. Okay, so let's go back to the track example. All right, here. If we have our scatter plot, your correlation coefficient is -0.84. Let's interpret the value of R in the context of the problem. So one of the important things to note is that R, your correlation coefficient, only talks about the strength and the direction. R does not tell you if it's linear or not. Okay, you want to put a star on your notes, circle this, something. R only tells you strength and direction. The picture tells you form. Okay, the picture will tell you linear or not. All right, so we can then interpret if you have negative 0.84, we know there's a strong negative relationship between sprint time and long jump distance, which we pretty much described last time when we described the scatter plot. B is now where we start applying more than what you learned in Algebra 1 or Pre-Cal when you guys learned linear regression. Okay, what effect does the point highlighted with a triangle have on the correlation? Explain. So what does this triangle do, right? Does it make your correlation coefficient stronger, or does it make your correlation coefficient weaker? Hopefully you said weaker, because it's farther away from the pattern of the line. If you had a line here, this triangle is away from the line. The farther away it is, the weaker it makes your correlation coefficient, okay, your correlation. So it would make it weaker. So the way I described it is here. I said, since the point is higher than expected on the overall pattern of the rest of the data, that makes the correlation weaker or closer to zero. The relationship it has with a correlation is the same as like saying the correlation coefficient. Correlation is relationship. How are they related to each other? Now, you might be saying, okay, well, Ms. McMichael, if you said we can skip this formula, are they always just going to give us this number? No, they're not. So if we go back to the calculator and we come here, all right, we're going to get that R from here. You're going to go Menu, Statistics, Stat Calculations. Pick this one, okay? Now, I know that you are used to seeing things in mx plus b form, right? Because that's the equation of a line. The grown-up way to handle statistics, you know, the AP way and all the colleges, everybody else uses a plus bx. So this is the one we use, okay? Keep in mind, your slope is still attached to the x, which we'll deal with slope later or next lesson, but we're going to pick this a plus bx every time. So your x, click in the center button. Our x is sprint. Our y is long jump, okay? We just want to make sure we're putting it in an empty column. So right now my columns A and B are full. So I'm going to change this to C, because C is empty. Because if you don't change it, it's going to overwrite what's in B and take it all out. All right. You will see that if you scroll down here, there's your R, negative 0.84 that they gave us. Be careful that you don't use R squared. We'll deal with that later in the next section. We want just the R. Also be careful on your calculator screen, this negative sign is really tiny. It's like barely a pixel. So just make sure that you use checks and balances. If your graph is negative, your R needs to be negative. Just, you know, be careful with that. So let's do another problem. Okay, so let's tackle this example. Okay, take a minute, plug in all the sodiums and all the fats for the 10 different salads, okay, along with the amount of sodium and fat in them. So you never type in the names, but these are all the salads. Okay. So now that you've typed them in, I gave you a scatter plot, but try playing around with the scatter plot as well. Okay, so play around with the scatter plot in your calculator. You can actually go to this page, and I'm just going to type in sodium on the X and fat on the Y. So here's my scatter plot, which matches the scatter plot that I put on your paper. Okay, you want to find your correlation coefficient. So you're going to go to your sodium and fat tab. You're going to go Menu, Stats, Stat Calculations, Linear Regression. Remember, you can just hit the 4. You don't have to tab through it all. We're going to have sodium be our x-axis, and we're going to have our y-axis be that. Okay, I'm going to check my results. Yep, good. Column C, press OK. There we go. All right. We will come back to this data in our following lesson, but here, our correlation coefficient is R equals 0.8498 is what I wrote down. Absolutely, you should go 2, 3, 4. The more decimals, the better your answer is. You should never make that 0.8. No way, no how. Okay, so we have as our description here, there's a strong positive and linear relationship between sodium and fat, meaning the more sodium, the more fat in the salads. Okay, and then I wanted you guys to find and interpret your correlation coefficient. So here's your correlation coefficient, and it is strong and positive. If you write linear here, that is a mistake because this graph cannot, the graph tells you linear, but R does not tell you linear. And how we can confirm that is, what I'd like you guys to do is then type in these. Make this your X column and make this your Y. Okay, go make a little data set of those, graph it, and find your correlation coefficient. All right, pause the video, do those things. And then if you watch me, all right, because I forgot to put them in. 7, boom. Right, was it 1, 4, 9, 16, 25, 36, 49, boom. All right, if I call this X and this Y and I graph this, okay, and I put my X here, oof, and I put my Y here. Oh, did I not name it? Y. I never pressed enter here. Y. Now I have Y. There it is. Okay, not linear. This should be, hopefully you recognize this as half of a parabola, right? I could go back and I could add more. So I could add 8 and 64. And it gets a little more pronounced. 9 and 81. Whoops, not 841, 81. Right, and I could do 10 and 100. Let's say I do that. Okay, now my graph, if I just zoom it again, zoom data. Zoop, there we go. Now we can really see that it's a parabola. Okay, half of a parabola. So this is clearly not linear. Okay, but watch. If I do my correlation coefficient, and I pick X for my X, and I pick Y for my Y. Okay. Notice my R. It's phenomenal. My R is really strong and really positive, but the graph tells me it's really not linear. That is absolutely curved. If I kept going, this would be a beautiful parabola, half of a parabola. Okay. So that's that reinforcement that when you're looking at graphs, okay, our description for this would be it's strong and positive, but this absolutely is not linear. Even though some people fall into a trap that here they're like, oh, R is strong, positive, linear. This is not linear, right? But it is strong and positive. All right. Have a good one. Nice job today. Do the bookwork. Oops. This bookwork is the important work for you guys to do today. Okay. Oh, it should be pretty quickly, right? Like you should be able to fly through it pretty quickly. All right. Have a good one.